For this video, I've highlighted some Laplace transform pairs. This is table 15.2 in the circuits book. We're going to perform some inverse Laplace transforms. Some of the transforms that get confusing involve sines and cosines. For example, let's take a look at when you have the function sine omega t and cosine omega t, which require you to follow this formula to get them back. If you have the function f of s equals 3 over s squared plus 9, you could compare it to the table and see that this would Laplace transform to f of t equals sine 3t. For the same reason, if you had f of s equals s over s squared plus 9, you could look at the table and see that this transforms to f of t equals cosine 3t. This is because the square root of 9 is 3, and this can be written as s squared plus 3 squared. So that matches our s squared plus omega squared that we have here. But what if you had f of s equals 2s plus 5 over s squared plus 9? This absolutely does not match this table at all, because there's no 2s plus 5 in the numerators here. So here's what we can do. Step 1 is to split this into 2s over s squared plus 9 plus 5 over s squared plus 9. You see that this is a little closer to the table because we have a term which only has s in the numerator and a term that only has the constant in the numerator. But for sine, the constant here needs to be 3, not 5. And for cosine, we just need s, not 2s. You may be able to guess what we need to do. We need to write this as 2s over s squared plus 9. And then what we're going to do here is we're going to pull out the 5, and we're going to divide by 3 and multiply by 3. So we introduce a 3 out of nothing. And now we have 2s over s squared plus 9 plus 5 over 3, 3 over s squared plus 9. And this can be inverse Laplace transformed into 2 cosine 3t plus 5 over 3 sine 3t. So this is one example for fiddling with a Laplace transformed function and inversing it back. Okay, we're taking that and we're shoving it elsewhere, and we're doing a new thing. And we'll do it in green. Suppose you had the function 3s plus 7 over s squared plus 2s plus 5. It's worth noting that this denominator cannot be factored into two smaller factors. It's just s squared plus 2s plus 5. Oops. Now, if we look at the table here, you can clearly see that there is nothing of the form s squared plus as plus b. The closest thing we have is this possibly familiar form to you, s plus a squared plus omega squared. This is a completed square form of a quadratic equation. So you may remember how to complete the square, but if not, let me give you a crash course. If you have a quadratic in this form, so there's no constant out here, and you have b and c, in order to complete the square, you need to figure out what to add to this box and subtract, you're introducing something out of nothing, so that right here is a perfect square. Now the thing you need to introduce to this box is b over 2 squared. If you do that, then this whole quadratic becomes x plus b over 2 squared plus c minus b over 2. Note that this is plus c minus b over 2, and then it's x squared plus b over 2 squared that gave us this thing right here. So for a specific example of that, let me give you x squared plus 4x plus 5. 4 divided by 2 is 2, 2 squared is 4. So we'll rewrite this as x squared plus 4x plus 4 minus 4. And then we have the plus 5 over here. Now x squared plus 4x plus 4 is simply x plus 2 squared. This is easily factorable, and 5 minus 4 is equal to 1. So we have successfully factored, or completed the square of x squared plus 4x plus 5 into x plus 2 squared plus 1. If you had x squared plus 6x plus 5, you would divide 6 by 2 to get 3 and add 9. So we have x squared plus 6x plus 9 minus 9 plus 5, which gives us x plus 3 squared minus 4. Now note that if this is a negative sign instead of a positive sign, then you need to introduce you introduce the same thing, but this becomes a negative sign. So let me just do one quick example of that. If you have x squared minus 6x plus 5, you still introduce 9. So we have x squared minus 6x plus 9 minus 9 plus 5. But this part factors into x minus 3 squared. And then you have minus 4 over here. So it's just the sign changes slightly. That said, we can now complete the square in the denominator here. s squared plus 2s necessitates that we add and subtract a 1. So this is 3s plus 7 over s squared plus 2s plus 1 minus 1 plus 5. And this is equal to 3s plus 7 over s plus 1 squared plus 4, which we will write as 2 squared for the time being. Now this looks promising because we have s plus a squared and omega squared in the denominator, but the numerator still doesn't match. We need to have an s plus a, in this case an s plus 1 in the numerator, or omega in the numerator, and we do not have either of those. So how on earth are we going to split up this equation effectively? The way I do this is to look at the s term and the constant term. Now the s term you can see is multiplied by 3. If we want to introduce s plus 1 to the numerator here, we need to have 3 times s plus 1. So we need to add, and so we need to bring out a 3. So let me show you specifically what I mean. We'll write this as 3s plus 3 plus 4, all over s plus 1 squared plus 2 squared. You may now be able to see what I mean. You see that 3s plus 3 is 3 times s plus 1. So let me factor that. Now you can see what I mean. So I looked at the constant in front of s, 3, and I knew I needed to introduce s plus 1. So I had to bring out another 3, so that when I factored out 3, I got 3s plus 1. And we're left with this 4 over here. And so I've now split this fraction into 2. We have 3 times s plus 1 over all this, plus 2 times 2 over all this. And you can see that that matches the pattern here. On the right side, we have 2 and 2, and then s plus 1 in the denominator. And here we have s plus 1, which matches this guy. So we can finish writing this as 3e to the negative t cosine 2t plus 2e to the negative t sine 2t. We have successfully split apart this fraction into 2 fractions, which can be immediately inverse Laplace transform. And sorry, this shouldn't be an equal sign. This should be an arrow sign with a little inverse Laplace on it. All right, so we are looking good-ish. There's one more caveat that is involved in splitting up a Laplace transformed equation and turning it back into its original Laplace transform form, and that's when this quadratic is factorable. This method is called partial fractions, and it is the subject of our next video.